Prachi Dubey. She is in her BSc Mathematics from Dr. Harsh Singh Gaur Vishwavidya Sagar, Madhya Pradesh. So, and her topic for the day is generating sets. Yeah, Prachi, over to you. You can share your screen.
Is the screen visible?
Yes.
Okay. So, good morning to all. Myself Prachi Dubey, and I am going to present the topic from algebra, that is generating sets and minimal generating sets for the groups. As the name suggests, we are talking about the sets which can generate the whole group. We have already seen this concept in linear algebra. We have the concept of a spanning set in basis. We have spanning set and basis are already discussed in linear algebra. So this is somehow similar to that. But we will discuss either the properties of the both are similar or not. So let us come to the basic definition, formal definition of the generating sets. Suppose in a group G, we have a subset of G, that is X. Then X can be the generating set for G if for every G belongs to G, that is every element of group can be represented as the product of the elements from X or its inverses. So here for another definition, we can also say that a subset X of a group is called generating set if the smallest subgroup containing X is the group itself. Then we can say the group is generated by X, and we represent it like this. So I have a question, that can elements of finite order generate the group of infinite order? I mean, it is possible or not?
No,
Uh,
it is not possible.
But what can you say about the power set of a power set of X when X is infinite under the operation symmetric difference? In that group, what is the order of every element? So in that group, every element has finite order, that is 2. Every element is inverse of itself. So, the power set defined on X, when X is infinite, then this group is of infinite order. But all the elements are of finite order. But the group consists of the elements of finite order. Then the group is generated by the elements of finite order. No? So it is possible. So after definition, we will discuss some examples. So the most basic example is the cyclic groups. We have studied about the cyclic groups, that is the group generated by a single element. So if we consider the group of integers under the group operation addition, then this is a cyclic group which can be generated by 1. So mm, it is necessary that a group have only one generating set. It can have more than one. It can have more than one generating set. So there are. We can find out other possible generating set for this group other than one. So I will discuss this later in this slide because it has another concept related to this. So for next we have the example of a dihedral group. Dihedral, we know that for n is greater than or equal to 3, dihedral is a non-abelian group. And a non-abelian group is also not cyclic, but it cannot be generated by a single element, but it can be generated by two elements. That is, it's any of its rotation and reflection. So every rotation is a combination of either rotation or reflections, and every reflection is combination of rotations and reflection. So every element can be generated by only two elements. So we have discussed two examples, and we can see that these are examples such that it have the finite generating set, that is the number of elements in that generating set is finite. So we can say if a group is generated by finite number of elements, then the group is finitely generated group. But what can you say about the generating set of R plus, that is set of real numbers under addition? Can you find an generating set for finite generating set for R plus?
Singleton one.
No, it cannot generate the whole group R. It will generate the set of integers. You will apply operation 1 plus 1, it will give 2, plus 1, it will give 3. It will not give the whole set R. So actually, we don't have any finite generating set for these two groups, even for R plus and even for R square plus. So in vector space, we have seen that R square, that is a set of two tuples on R, that can be generated by 1 0 and 0 1, but it is not true in groups. Why? So can anyone? Okay. So in vector spaces, we have a linear combination, that is we multiply 1 0 0 1 with some real numbers, that is the scalars. But in group, that is different in group. If we try to generate that R2 with 1 0 and 0 1, that every element of R2 can be written as the form of some x into 1 0 plus y into 1 0, where x and y are integers. So in group theory, we can only generate the set of integers, that is a set of integers by uh, mm, these two tuples, that is 1 0 and 0 1. So it is different in group theory and in vector spaces. So as we can see, we have find out the group which is not finitely generated. So when a group is not finitely generated, that is it have infinite number of generators, so it will called as the infinitely generated group. So I can you tell about the an element of infinite order can generate element of finite order? I mean, such A is an element which have infinite order. So can there exist B such that A to the some power is equal to B? Okay, so uh, suppose if we consider that a to the power some uh, p is equal to b, and b is of finite order, then what we conclude that a should be also of some finite order, because b to the power some integer will be equal to b to the power some positive integer will be equal to identity, so it will be multiple of p. But it is not possible, but it is possible when b is equal to identity. So an element of infinite order can generate the element of finite order if and only if the element is identity. I mean, the element of infinite order can only generate the identity element. So we have one remark, that every finitely generated group is countable. We can write every finitely generated group as we can write explicitly the elements of finitely generated group. So every finitely generated group is countable. So an uncountable group cannot be an uncounted and every uncountable group is infinitely generated. But what about the converse? That is, every countable group is finitely generated or not?
No, it is not true.
So can you give an example?
Rational numbers.
Yeah, you're right. If we consider the set of rational numbers under addition or under multiplication, and the set of non-zero rational numbers under multiplication, then the group is countable. But we can easily prove by contradiction that this group does not have any finite generating set. So, some few examples that we have to find that are these finitely generated or infinitely generated. So if we talk about the power set of x under the operation symmetric difference, so when x is finite, then the power set of x will be the group with finite order. The order of group will be 2 to the power that cardinality of x. So we have already discussed that if the group is finite, then the group can be generated by the group itself. I mean, the whole group itself is a generator. So group is finitely generated. But what if the x is infinite? So, if x is infinite, then the power set of x will be uncountable. By we can see by Cantor's theorem. Then, when the x is infinite, that the power set of x will be the set with will be the set uncountably infinite. So we have seen that an uncountable group is always infinitely generated. And symmetric group Sn under the composition of functions. Since symmetric group is the group of permutation defined on and symbol, so it is also finite group. So a finite group is always finitely generated. Now, what about the special linear group of order 2 under with entries of integers? So, special linear group with order 2, with matrices of order 2 and entries from Z integers can be generated by only two elements. These elements are 0, -1, -1, 0, and another element is 1, 1, 0, 1. We I have not described the proof here, but uh, the proof can be seen by using the uh, Euclid's lemma, Euclid's division algorithm. So I think you should try. And about the general linear group with entries in R and having matrices of order n cross n. So in this group, we are taking entries from real numbers. Since the entries are from real numbers and R is itself uncountable set, so GLN R will be also the uncountable set. So this is also infinitely generated. Now we can talk about the concept of minimal generating set. Like we have basis, which is a subset of a spanning set in vector spaces, such that by removing an element of the basis, the set is no longer the spanning set. Just like that, we if we have a generating set x, and that is the minimal generating set, then if we remove any element from that minimal generating set, then the set is not able to generate the whole group. It will generate some subgroup of the group, but it cannot generate the whole group. So minimal generating set is quite similar to the basis, but does it have the same properties like basis of a vector space? So the question is, we know that every vector space have the same number of element in all of its spaces, and but can do we have same number of elements in minimal generating set of every group? And similarly, we know that every subspace of a finite dimensional vector space is also finite. So is it true for subgroups of finitely generated group? And also we can check that if we know that if a subspace is a proper subspace of vector space, then dimension of that subspace is strictly less than the dimension of vector space. So the question is that is it is also true in groups also. But so let us consider the example of symmetric groups on n symbols. We will try to understand this concept of minimal generating set with this example. So since symmetric group is the set of all permutations on n symbols, so Sn can be generated by its transpositions. How we can see that for n is equals to 2 it is obvious, but for n is greater than or equal to 2, we can n is greater than 2, that is n is greater than or equal to 3, we can always write the identity element as the combination of as the product of transpositions, and we can always write the 2 cycle is itself a transposition. But what if the cycle is of order 3 or more than 1? That is, so we know that every permutation is a cycle or a product of cycle. That is, every element in the Sn is either a cycle or a product of some disjoint cycles. So we have the product of cycles. Suppose we have a product of cycles. So we have to show that for a k cycle, we can write it as the product of transposition. So we can see that if we have a k cycle I1, I2, Ik, then it can be written as the product of transposition I1, I2, I2, I3, I3, I4, and Ik minus 1 to k. So this is true for all. So Sn can be generated by all of its transposition. So here we have the set of all transposition as the generating set for Sn, and the number of elements are n square minus n by 2. But the question is that do we need all the transpositions to generate Sn? Can we reduce the number of transposition, or we can eliminate some transpositions from that set? So yes, we can eliminate the sum of the transposition and reduce the number of elements in the generating set. So the next is Sn can be generated by n minus 1 transpositions. That is, either the transpositions are of this form or they are of this form. So for this form, we have already shown that Sn is generated by set of all transposition. So we have to show that arbitrary transposition, that is of the form ij, can be written as the transpositions of this form, that is I some ik. So ij can be written as I, 1j, and 1i. So ij can be written as a product of such type of transpositions. So now we have reduced the number of elements for Sn to n minus 1. Now for this type of form, we can prove that by induction. That is, we have 1k. If we have 1k, for k belongs to 3, 4, 5 up to the n. So 1k can be written as the 1 to 2k cycle 1 2, and 2k can be written as the product of 2 3, 3k, and 2 3, and so on. After the repetition, we will get at last we will get the transposition like 1 2 k minus 2, k minus 1, and which is similar to the transpositions like of this form. So we can convert from so we can get this such type of transpositions from this type of transpositions. Now we have a number of elements in this set is also same as the previous one, that is n minus 1. So uh, is there any other set which can generate Sn? So yes, we have another set which can generate Sn, but it cannot be but this set, that is the set of transposition of the form I plus 1, we cannot reduce this set, because if we reduce this set, then it will not generate the whole group. But it is possible to reduce this set and add some another element. So if we have a lemma that for a k cycle, arbitrary k cycle I1, I2, Ik in Sn, and arbitrary sigma, that is a permutation in Sn, we sigma of product of sigma k cycle and sigma inverse is equal to the cycle containing sigma I1, sigma of I2, sigma of Ik. So we have already proved that the Sn can be generated by the transpositions of the form I and I plus k. So if we consider the sigma as n cycle, that is 1, 2 up to n, and the transposition we take is 1, 2. So if we apply the lemma to it, that is sigma 1, 2 of sigma inverse, it will generate 2, 3, and like that it 2, 3 will generate 3, 4. So that is we are applying the lemma on 1, 2 for k times. For k belongs to 1, 2 up to n minus 2, we will get all the transpositions like 1, 2, 2, 3, 3, 4, and up n minus 1 up to n. So here we can generate a whole group by just two elements, that is 1, 2 and n cycle. So we have seen three different we have seen four different generating sets for Sn. So first of all, we have to check that how many of them are minimal generating set. So I have already told that x1 cannot be the minimal generating set, because we have removed some number of transpositions, and after that it is also the generating set. But for x2 and x3, if we remove any transposition, suppose S4, if we consider S4, we have the transposition 1, 2, 2, 3, and 3, 4 as the generating set. So if we remove one of them, then it cannot generate the whole S4, because we have two disjoint cycle. Sorry, 1, 2, 2, 3, and so if we remove 2, 3, then we have 1, 2 and 3, 4. So we have two disjoint cycles. Since we know that the two disjoint cycles are always commute, so sorry. mm, so S4 should be abelian. No, actually. So basically, that if we remove one of the transposition, then it cannot generate the whole group. So if we talk about x4 is the minimal generating set having n cycle and transposition 1, 2. So we can see that we have different minimal generating set, that is x2, x3, and x4. So x2 cardinalities of x2 and x3 is n minus 1, but cardinality of x4 is 2. So we have different cardinalities for the different generating sets of the same group. So we have talked about the non-abelian group, that is Sn for n is greater than or equals to 3, that is always non-abelian. But what about the but what about the abelian groups or the cyclic groups? I mean, is it necessary that we can find any example for abelian groups or cyclic groups that have different number of minimal generating set? Then yes, we can find that. I have talked about the set of all integers under addition, which is a cyclic group, which can be generated by a single element 1. But we have a Bezos identity. By Bezos identity, we know that if the set of all integers can be written as the linear combination of co-prime sorry we two co-prime integers. So if we have p and q are integers such that both of either nor of them is equals to 1 or minus 1. So if p and q are co-prime integers, so the set x is equals to pq, that is the set of two co-prime integers can always generate the set of all integers. So here x is equal to 1 can also generate the set of all integers, and x is equals to pq can also generate the set of integers, and both of them are minimal generating set. So we have found an example such that a cyclic group is having two different sized minimal generating set. But what about a group of order prime? I mean, if a group is of prime order, then what can we say about its minimal generating sets? So, if a group is of prime order, then we know that its generators are other than identity. All of the elements of the group are its generators. That is, the number of generators are p minus 1. So, since all the elements are generators, so every single element can generate the group. So, in that case, minimal generating set will always have the same cardinality, that is 1. So, next,
It is 11:29. So maybe can you wind up in 5 minutes?
yeah, I will bind up in 5 minutes.
Yeah.
So, can you give some example of groups which have a unique minimal generating set? I mean, it does not have any minimal generating set other than only one. So, if we consider the trivial group, then it have a minimal generating set, that is empty set. An empty set can generate the trivial group of and obviously if we talk about the group having two elements, that is identity and some element a, so it also have a unique minimal generating set. It cannot be generated by uh, any other element other than one. So it I have in last I will talk about the applications of these generating sets. So generating sets are used to draw graphical representations, and one another concept which is used along with generating set is relation. So relation is somehow the like that the relation between two elements. That is another concept. So generating sets which they provide the method of representing the groups in uh, graphical representation. They provide the method to visualize the groups. And Cayley digraphs are drawn using generators. So these are applications of Cayley digraphs. These are used as natural model for interconnection network in computer design. So basically, this concept is useful in interconnection networks or some computer applications. So at last, I have referred the expository article of generating sets by Keith Conrad, and the books Contemporary Algebra by Joseph Gallian, and a first course in Abstract Algebra by John B. Freilich. So thank you so much. I have completed my presentation.
Yeah. Any questions from the audience of this meeting? Yes. Then let us thank the speaker. Thank you, Prachi, for the presentation.